More than two events. It is not obvious at first sight how the independence of three or more events should be defined. We could require that the probability of A1 intersect A2 and so on intersect AN equals to the probability of A1 times the probability of A2 times the probability of A3 and so on times the probability of AN. This in itself is not a very strong requirement, however, it holds whenever the probability of A1 is equals to 0, no matter how strongly the other variables depend on each other. To have some more local conditions, we can add the requirements that the probability of AI intersect AJ is equals to the probability of AI times the probability of AJ for OI not equals to J. However, consider the following situation. We select a positive integer from 10 braces at random. Let A be the event that this number is odd. Now let us select an integer from 20 braces at random and let B be the event that this number is odd. Finally, let C be the event that the difference of the two selected integers is odd. It is then not difficult to verify that the probability of A is equals to the probability of B is equals to the probability of C, which is equals to 1/2. And also the events A, B, and C are pairwise independent. That is, any two of them are independent. However, the probability of A intersect B intersect C is equals to 0, which is not equals to the probability of A times the probability of B times the probability of C, which is 1/8. Therefore, we do not want to call these events independent either. We resolve these possible problems by requiring a very strong property for a set of events to be independent. Definition 15.14, we say that the events A1, A2, A3, and so on to AN are independent if, for any non-empty subset S equals to the set I1, I2, I3, and so on to IK, which is subset equals to the n braces, the equality, the probability of AI1 intersect AI2 intersect AI3 and so on intersect AIK is equals to the probability of AI1 times the probability of AI2 times the probability of AI3 and so on times the probability of AIK holds. We close this section by mentioning that theorem 15.13 is easy to generalize to more than two conditions. Theorem 15.15, Bayes' theorem, general version. Let A1, A2, A3, and so on to AN be events in a sample space omega, so that A1 union A2 union A3 and so on union AN is equals to omega, and AI intersect AJ is not empty if I is not equals to J. And let C, which is a subset of omega, be any event. Then the probability of C is equals to the summations of the probability of C conditioning on AI times the probability of AI, where the summation is summing with index starting I equals to 1 to I equals to n. And the proof is very analogous to the proof of the original Bayes' theorem, so we just omit it here.